Hello and welcome to the eOrganic webinar, Undercover Nutrient Investigation, the Effects of Mulch on Nutrients for Blueberry. My name is John McQueen. I'm a coordinator for the eOrganic project. eOrganic is the organic agriculture community of practice with e-extension. We are a community of cooperative extension service personnel, researchers, ag professionals, organic certifiers, and practitioners. You can find the recording of this webinar as well as articles, videos, and more by going to our website at www.extension.org/organic_production. If you have a question for today's speaker at any time during the webinar, just type your question into the question box on your screen. We will review questions at the end of the presentation. We are excited and privileged to have with us three researchers from Oregon State University. Dr. Dan Sullivan is Research and Extension Soil Scientist in the Department of Crop and Soil Science at Oregon State University. Dan's research and extension program seeks to develop value-added uses for organic materials and to assist farmers and agribusiness in implementing effective and economical nutrient management practices. Dan joined OSU in 1995 and has had the opportunity to serve as an advisor for over 20 graduate students and is the author of over 20 extension publications. Luis Valenzuela is a postdoctoral researcher in the Department of Horticulture at Oregon State University. He previously graduated from the Horticulture Department at Penn State, where his research focused on plant physiology with a strong emphasis in root systems. Presently, he is doing research with berry crop root systems, including blueberries, cranberries, and raspberries. Ryan Costello is a graduate student pursuing a dual master's in soil science and horticulture at Oregon State University. He is focusing his research on the use of compost in organic blueberry production. He has experience in international agricultural development and a degree in interdisciplinary natural sciences biology from the University of South Florida. I'm now going to turn things over to Dan.
All right, thank you, John. It's a pleasure to be able to tell you a little bit about our ongoing project with organic blueberries. The project is a part of the OREI grant. It's an integrated grant that was funded by USDA National Institute of Food and Agriculture. And this is kind of the end of the first year of our project, and we have 2 more years to go. So we're telling you today about methods we're using in the project. We don't have a lot of data that is ready for application yet. So a little bit of outline of what we're going to be covering today. First, I'm going to tell you a little bit about the project as a whole. Then Luis will tell you about his underground camera work. Ryan will tell you about the development of an alternative compost specifically designed for blueberry. And then finally, I'll tell you some more about nutrient monitoring that's going on as part of the project. The PIs on the project include Bernadine Strick from Horticulture. Bernadine works with the overall management of the trial. Myself and Dave Bryla. Dave is Luis's advisor in USDA, and also Clark Sievert, Extension Ag Economist, is part of our project team. And a number of other research assistants and graduate students have worked on the project. Some ideas about where we are and where we're going. The actual field trial was planted in the fall of 2006. The project that is currently funded by USDA runs from 2008 through 2011. Our underground nutrient measurements we're going to tell you about today began last year in 2009 and will continue for 2 more years. Ryan's work with the compost began this summer and is scheduled to go on for 2 additional years to look at plant effects. So the project was really designed based on questions that came up with organic blueberry growers. There are a number of choices that you can make in terms of how you set up an organic blueberry planting, and because it's such a long-lived crop, those decisions are with you for a long period of time. So that makes research like this important because there's a big investment in establishing an organic blueberry production field. So the questions that the growers had was, what's the best overall system for organic blueberry production? And specifically within that, blueberries are traditionally grown here in Oregon on raised beds. There have been quite a bit of flatbed planting going on the past 10 years. So for organics, the question is, do you want a flatbed or a raised bed? Blueberry growers said that their number one problem was weed control. So we have included in the trial a geotextile weed mat versus sawdust as a weed control strategy. And then finally, fertilizer sources and rates. If you're in organic, there's a much different selection of fertilizers than you have in conventional agriculture. So as far as our overall design in the field, we have a factorial combination of all these factors. We have flat beds and raised beds, sawdust or weed mat, 2 fertilizer sources, and 2 fertilizer rates. Here's a shot of our field trial, and what you can see is that we've got a raised bed on the left here. Straight ahead, we've got a flat bed. Our individual treatment plots, here's one in the front that has weed mat. Here's one behind it that has sawdust and so on. These are all irrigated with drip irrigation tubes that are placed either side of the blueberry row. Closer view, flat bed on the left, raised bed on the right. You can see they make a pretty large bed to plant the blueberries in with the raised bed system, and that's primarily for increasing the longevity of the plants, and there are a number of benefits of it, and the plant scientist will tell you more about that in the next presentation. We're going to tell you about the underground nutrient story today. So in an individual field plot, there are 6 plants, like is shown here. The tools of investigation that we're going to be talking about today are different than we use in traditional soil and plant tissue testing, in part because blueberry is a unique crop and we're not wanting to disturb the plants. We want to disturb the plants as little as possible, so we're using a very small porous lysimeter called a Rhizon soil solution sampler. We're also using plant root simulator probes, PRS probes. These are small plastic tools that have a negatively charged exchange resin. These are placed into the soil. The advantage of using these to extract nutrients from the soil are that they act similar to roots. All of your nutrients that are being taken up by the blueberry plants are soluble in a soil solution, and they are either positively or negatively charged. So the way this system works is there's an orange probe that's negatively charged and another probe that's positively charged. So with those different, the other technique that Luis will tell you about is the mini rhizotron. This is a very small camera that is inserted under the ground to take a look at where roots are and their activity. So this This shows you in the field where we're placing these tools relative to the plants. Over here is the mini rhizotron access tube. That's where the little camera is inserted below ground. Here's a rhizon tube peeking out of the ground. That's where we hook up and put vacuum there and extract. And then finally here's the PRS probes, which have been fully inserted into the ground. Another shot of the configuration of the measurement tools relative to the plants. Again, here's the mini rhizotron tube sticking out and a few rhizon tubes collecting soil solution. Didn't want to forget that we have a lot of people involved with this project, a number of local funding sources that provided and continue to provide support for the project, an advisory board that has helped us with the experimental design and continues to advise as we conduct the project, and a number of collaborators on and off campus. So that wraps up my presentation, and I'm going to turn it over to Luis, who will tell you a little bit about our the underground cameras and that part of our nutrient investigation.
Okay, thank you, Dan. Thank you all the attendants to the webinar. Well, I'm going to talk about the using of the mini rhizotron tubes to study the blueberry root dynamics. And well, the first thing that I want to talk about is I wanted to explain how the mini rhizotron tubes technique work. And pretty much the mini rhizotron tubes are transparent acrylic tubes. They can be different in diameter or different length. It depends on the study. They are inserted into the ground, as you see in the pictures before. And the bottom pretty much is sealed, and the upper section is sealed with a removable rubber stopper, so we can use as access for the camera. And well, the camera, we call it mini rhizotron camera, and it has a similar diameter as the tube's inner diameter. And pretty much is, well, the camera is connected to a laptop computer that has special software that allow us to capture the digital images. And pretty much what we capturing is the roots are growing in the tube's surface. And the images are captured at 12 o'clock. If you see the tube, that's where we're doing a column of images going from the surface of the soil to the bottom. And well, the idea here is to collect images of the same spot over time, so we can have a history frame of what's going on with the roots. And what I'm going to do next is I'm going to talk about the technique in a chronological way using our study. So pretty much the first thing that you need to do when you want to use this technique is install the tubes. And we installed the tubes in winter 2008. We have a total of 90 tubes. We use, you see in the picture myself, I'm installing a tube there in a raised bed. And we use a soil coring system. And we make a hole the same diameter as the tubes. And once the hole is done, we pretty much insert the mini rhizotron tubes. And well, the tubes needs to be covered with a PVC pipe cap, you see there, to prevent the light to going in. And the treatments that we have that we're looking at are raised beds and flat beds with weedmat, like in this case, weedmat and for Duke. We have 2 tubes per plant, and we have 5 reps per each treatment. And we're also looking at also raised beds and flat ground systems using sawdust as a weed control. And also we have 2 tubes per plant and 5 reps. So once the tubes are installed, we collect images, and this happens twice or every 2 weeks during the summertime and once a month during the winter time. You can see here I'm taking some images and how the camera goes into the tube. And I'm going to have another image here. This is a screen computer, and you can see some roots there and how pretty much it's a video, and we pretty much capture that video into a digital image. And well, when we collect the images, you can see here this is an example of one particular point in one of the tubes. And we can see, we can track the changes in the roots over time. And until now, we have more than 55,000 images already collect that we need to analyze. And well, once we have the images, we transfer them to a lab computer, and we do the image analysis. So the image analysis is completed using a special software. And you can see, I just want to explain a little bit here. Those images are very, very small. They're 6 millimeters long and 4 millimeters high, and this is just because blueberry roots are very, very fine. Some of the roots are, the finest roots in blueberry can be 20 microns in diameter. I'm talking about roots that are smaller diameter than your hair. So we want to be sure that we can measure those roots. So the way this software works is once we found roots, we can track them, and we can measure the length. You can see the green line is measuring the length of that root, and we also measure the diameter. We can also measure the color of the roots, and all these happen. We can do that over time. And see, in this case, and you're going to see a change here. We increase the image here because we wanted to try to be able to get more roots, and this image was a little bit increased. But it doesn't mean that we can continue doing the tracking of the roots over time. So I'm just going to move pretty fast just to show you what's going on with the roots. And well, the point here is just to show you how we do the work. We usually track all the roots in an image. Every single root, we usually mark them and measure them. In this case, we have only 2 roots, but we try to do all of the roots. In this case, you see there is the circles are filled with a brown. That means that the roots turn in a brown color or pigmented, and the second root, the smaller root, we mark it as dead. And this image was taken in December. So what type of information we can get doing all this analysis? Well, as you see, we can measure root diameter. We can measure the order of or position of the root in the branch. We can measure color or pigmentation, and we also can assess or calculate the age of the roots. And all these aspects are very intimately related with the physiology of the fine roots. We're trying to understand how the roots work in the different systems that we have. So I'm just going to go into some details or explain to you what type of information at the end this research is going to give to the public and to the growers. So the first thing is root production. We can estimate root production. We can also estimate changes in root function with age and root lifespan. The first example talks about root production, and this is another research that was done with by Comas et al. In 2005, and this is with grape. The only thing that I want you to see here is that we're looking at those peaks of root production, and pretty much that means that we're seeing new roots growing. In this case, with grape, we're seeing new roots growing in pretty close to the verizon time when the grapes were turning blue. And I'm going to explain why it's a very important reason to know when new roots or young roots are present in the soil. There is a very good relationship of root age and root function. as I'm going to show you next. There was a research done also by Comas with grapes, and you can see this picture. It was pretty neat research because they were able to link the mini rhizotron images. Here you see pretty wide roots, new roots, and they were linked. They pretty much have those roots in the same stage and do some assessments of physiology. And they found that new roots, or wide roots as we see in the picture, have the highest physiological activity compared when you have roots that turn brown, or either when roots turn black, that the physiological activity of those roots diminishes very strongly. So that's why we're trying to find when these new roots are growing. And I'm going to show you why. This is another example with grape, Volter et al. In 2005. They just they did an experiment and they found that the young roots that are less than a week old have the highest nitrogen uptake capacity. And also it was found not only in grape but also in citrus in another experiment when young roots also have the highest phosphorus uptake capacity. So it's very important for us and for the nutrition part of to know when these new roots are. So we can apply fertilizer, scheduled fertilization in a better way. So root lifespan is pretty much how long the roots stay alive in the soil. And with this technique and with all these measurements, we can assess, or we can include once we run the statistics, we can include in the model how fertilization, irrigation, soil depth, soil temperature, yield, or soil pH affect the lifespan of the roots in the soil. So until now, we don't have, as you see, we just started the experiment last year, and we have thousands of images that we need to analyze. That takes a long time, so we don't have results right now. But just as based on visual observation, we saw kind of like a peak of root. We saw new roots growing right after harvest time, and we also saw some differences in the raised beds compared to the flat ground beds. That we see more frequency of new roots growing in the bottom part section of the raised beds compared with the upper section. And I guess this is pretty much because of the raised beds are getting a little bit drier during the summer on the upper part than in the bottom part. So I think that would be, if you have some reference, that would be the end of my presentation. Thank you very much. And I think I'm going to give the microphone to Ryan.
Okay, thanks, Luis. My name is Ryan Costello. I'm a grad student at Oregon State University. As John said, I just started my research last summer, and I'm working under Dan Sullivan in soil science. So I'm looking at composting and blueberry production, and just to begin with, I'll give a brief overview on making a compost, which is something I worked on last summer. So there we go. So the goals of a good compost mix, moisture should be around 60%. What I found last summer is that by hand, this is trying to get the compost to the point where it's like wringing out a damp sponge. Carbon to nitrogen, usually in the range of 20 to 1 to 40 to 1, ideally in the range of 25 to 1 to 35 to 1. Aeration, you want to get the aeration to, I'm sorry, let me start over again. It's an aerobic process as composting, so you want to allow proper aeration into the mix. There's several ways of doing this, but the two most common, passive and active ways, active being turning the compost frequently, and passive being using things like a tube or other types of ventilation systems that allow air to pass through the compost. And At the end there you can see proper bulk density. Usually you want to shoot for around 1,000 pounds per cubic yard, but bulk density, oftentimes something that you can guesstimate. You just want it to be dense enough for the compost to be able to heat up, but not too dense to prevent aeration of the compost in the aerobic process. So when a compost goes anaerobic, you can tell, usually get like a slimy byproduct, and you can tell also by the smell. So Washington State University is working on developing a compost calculator, and we've been trying this out. Last summer we made some mixes based on this calculator. And what it just allows you to input the carbon to nitrogen ratio of the various feedstocks that you're making your compost out of, and it kind of gives you an idea of what the final mix looks like, what kind of range you're in for moisture and for carbon to nitrogen ratio in the final mix. There are certain books like the On-Farm Composting Handbook that can give estimates of the feedstocks, the carbon to nitrogen ratio average for various feedstocks, but you can also do analysis of those feedstocks to get a very specific carbon to nitrogen ratio. So that will help you to create a better mix which will heat up better, be more consistent. So in our research, we were trying to find a custom compost for blueberry production. So out here in Oregon, as Dan said, blueberries have grown traditionally in Douglas Fir sawdust. It's a softwood, and it's very acidic. So the blueberries tend to like what we call like a fluffiness, and they just like a lot of organic matter. And so the sawdust provides that kind of fluffiness, and the soil provides all that organic matter for the roots to grow through. Also, and has been theorized, it makes the soil or that region around the roots more acidic, which the blueberries prefer. But there are some problems with sawdust. One of the major ones is that it's highly immobilizing of nitrogen. So as the microbes try to break down the very high carbon sawdust, they actually take nitrogen from the soil that surrounds it, could even take nitrogen from the fertilizers that are applied to the blueberries. So the consequence of that is that we believe that often farmers are applying more nitrogen especially than would be needed for the blueberries. And also sawdust around here is becoming less available, more expensive. So farmers are looking for alternatives, and that's why we're looking at compost. So we're analyzing locally available compost, and we're also trying to create our own custom mixes and looking at what are the characteristics of different kinds of mixes we can create. So locally available feedstocks around here are spoiled hay, vegetable waste, dairy solids. These are all feedstocks that we've gathered from around the area. Mint hay, leaves, yard debris, spent hops, grape pomace, and filbert husks are all available around here. Many of these are almost like waste products that can be gotten for free. So over the summer of last year, I created 10 different compost mixes using these bins. It's like what we call a modular system of composting. And so basically we made mixes out of these locally available feedstocks, put them into the bins, and use like a passive and an active aeration. So the passive part was these perforated pipes that are at a 45-degree angle in the bins, and the active part is that we're dumping out the bin and mixing them once a week. So as we tracked the temperatures of these bins, we felt like we were pretty successful in getting them to heat up. They all got over 50 degrees Celsius for at least several weeks, and you can see some of the temperatures on the graph at the bottom. Pretty much all the composts were finished with the active composting phase within a month. Some of them went a little bit longer than that, but they are also smaller piles because of the size restriction of the bin, whereas a much larger pile might heat up for longer. The bins allowed us to keep the compost separated from each other so that we could actually analyze what are the characteristics of this particular compost, so the bins just made that easier, more convenient. So in designing a compost, we had a lot of different questions that we're trying to answer. One of them is we know blueberries prefer acidic soils, but we don't really know if they prefer acidic compost. And so another question that we have is looking at the compost, and you can see the analysis on the right-hand side of the screen there. This is just a few different composts. The ones at the 4 at the bottom are ones we gathered, and 3 at the top are the ones we created. There's quite a range of pH and ECs, but the pH usually ends up around neutral, and oftentimes it's over 7 for older composts. So you can see anywhere from 6.5 to 8.5, but usually around neutral. It's very hard to design a compost that actually comes out at the end of the composting process acidic, and that's just because of the nature of what the organisms do. So we know that from what we know about blueberries, they are sensitive to high salts. We don't know what the limits of that sensitivity are very well, but we do know that they are sensitive to that. And compost, as you can see on some of these analyses, can get quite high in the salt and the salinity. So that is one of our questions. How much would a blueberry tolerate or prefer as far as compost salinity? You can adjust for the salinity depending on what kind of feedstocks you use to make the compost. So, for instance, a compost made with a lot of manure would have higher salinity. So I've been doing experiments in the lab looking at acidifying compost. Usually you would use elemental sulfur in the field. In the lab we're trying H2SO4 just to try to predict how the compost will respond to elemental sulfur in the field. Salinity does increase as the pH decreases, something we found in the lab and something that we know from the literature. And so I've been doing a lot of different titrations with H2SO4 and have trials planned with elemental sulfur to see how these H2SO4 titrations predict the response of the compost to elemental sulfur. So what we found is the acid was added. It's a fairly linear drop in the pH, but the composts do have different slopes in the way that they respond to the acid added. And the EC rises in a fairly linear fashion as well for the various composts. So the research plans for this year are basically to be trying to refine the lab techniques for predicting the sulfur response. That's the H2SO4 titrations. We're also going to be trying elemental sulfur and seeing how our predictions hold out with elemental sulfur in the field with the various composts. And we'll be doing plant trials in the greenhouse this winter and then possibly in the field over the summer, and looking at some of these composts, acidified and non-acidified. We want to know, did the plants prefer the acidified versions, or how do they respond, and also, how do they respond to some of these more saline composts and things like that. Basically, we want to know what the plants prefer. So if you want more information on composting, the on-farm composting handbook is really handy. That's something I've been referring to a lot. So thanks so much, and I guess I'll hand it over to Dan.
Yeah, so the next thing we want to talk about is the below-ground monitoring with the Rhizon tubes and the PRS probes. These are alternatives to traditional soil testing, and the reason why we use them with blueberry is because of the difficulty of punching a lot of holes and doing traditional soil sampling. Also, since we're studying roots, we want to modify the area near our mini rhizotrons as little as possible. So the rhizon allows us to put a vacuum on the soil, extract soil solution. Soil solution is a direct measure of what the plant has access to. So it's measuring the actual concentrations of soluble nutrients, pH, and salts. After the installation, it is easy to do repeated measurements using the same tubes that are in place. These tubes typically don't last forever, but we hope to get several years out of the tubes installed this year. Some of the limitations of this technique, you can only sample soils that are moist enough to extract soil under a vacuum. So basically, if your soil is dry, you'll get no soil solution. There is some root disturbance when you install the tubes, so immediately after installation we expect that there might be some effects of that disturbance. Typically it takes over a day to collect the samples, so you might have to go to the site and begin taking the samples and then come back and get the finished samples the next day. It's not really calibrated for routine soil testing, so there's no tables you can go and look up and see what is an appropriate number for concentration of a particular nutrient. And then, as with all soil sampling techniques, we only get to sample a very small volume and we make inferences for the whole field. So some background using this tool. Luis is actually the guy that goes out and does this sampling. And the group that Luis works with, Dave Bryla and his other students, Oscar, they've been doing work with conventional blueberry production where they apply chemical fertilizers like urea, and they found with urea that if they apply a modest rate of nitrogen, 60 pounds of nitrogen per acre, split into 3 applications, that they get soil solution values that peak at 2 to 3 millisiemens per centimeter. So that's the same units numerically as millimos per centimeter. That's a more common unit for practitioners. So that's a potential problem because blueberries, according to the literature that's out there, are sensitive to salts at a level around the level you get with these commercial nitrogen applications. So as far as we know, this is some of the first work looking at actual concentrations in the field with high bush blueberries. All right, so the other tool in our arsenal is the plant root simulator probe. This is a patented device. We obtained these from Western Ag Innovations. They have a very informative website that will give you all kinds of information on their probe. Basically, it is a very durable exchange film. This shows you the size of the little stakes that go in the ground. These are placed into the soil, and the idea is that you've got a positively charged probe that will sorb nitrate, phosphate, sulfate, and borate, which are negatively charged ions. And you've got the opposite over here. You've got a negatively charged purple probe, which sorbs all of your positive ions, ammonium, potassium, calcium, magnesium, and some of the micronutrients. So the advantages of this for an organic system are that unlike traditional soil testing, we don't use any extractions to remove the nutrients from the soil. We're actually doing this in the field, so it reflects actual field conditions. We're able to get a look at a broad scope of these nutrients in one extraction procedure. And it's a pretty simple tool for use in terms of getting the samples from the field. And we're looking at a measurement that integrates over time, so we're not just measuring what's happening today, we're getting a measurement that's a little bit longer term. Some of the limitations, as with any tool, there's limited calibration information, so we don't really know for sure what is low, medium, and high nutrient content in terms of crop response. So right now this is mainly useful as a tool to evaluate relative differences in nutrient supply rate. And as I mentioned before, there is a question about how many of these probes you need to represent average nutrient flux as it affects the plants. So kind of the dance that we do in terms of using these probes, they're inserted into the soil, keeping the probe in good contact with the soil. So it's there for 2 weeks. We come back and remove the probes and put a new set of probes in for the next measurement period. The probes we take out have to be washed very carefully to remove the soil and sent to a lab for analysis. So there is some turnaround time in between the extraction of the tube in the field and when we actually get numbers. So this is another part of the reason why it's, at the present time, it's a better research tool than an on-the-go nutrient decision-making tool. So the reason why I chose this as part of our project and approach to looking at the nutrients in blueberries was because I think that it makes a difference when the nutrients are available and we're measuring the root growth. So we want to kind of see what the timing of the availability of the nutrients is relative to the root growth, which Luis is measuring. On a very similar kind of a soil in the Willamette Valley in Oregon where we are, Steve Salisbury and Neil Christensen did a study using these probes to follow nitrogen availability following a clover or an oat crop. They were growing winter wheat and looking at the rotation effect. I'm just showing you this because it illustrates the utility of these kinds of probes in looking at the timing of nutrient availability. So here we are in the fall, right after winter wheat was planted, probably about the middle of October, and we can see that we get the big effect of nitrogen availability from the cover crop. The green is clover, the blue is after oats. We get that effect early in the fall, and by later in the fall, the values are pretty similar for either the oat or the clover cover crop. So that tells us something about how the plant is being treated in terms of nitrogen supply. It turned out in this study that there was a big difference in eventual grain yield just because of this short period of increased nitrogen supply. So in today's discussion of our actual data, I want to highlight the effect of the mulch, comparing the sawdust versus the geotextile weedmat mulch. We have many other comparisons that we could talk about, but these are the ones that are the most pertinent with the data we have to date. So in terms of the data we're looking at plots that received either 25 or 50 pounds of nitrogen per acre with the fish applied on 2-week intervals. So there were 5 applications of 5 pounds per acre of nitrogen per application. And during each 2-week period after fish application, we monitored the nutrients with PRS probes for the whole period, or took 6 samples of soil solution using the Rhizon samplers.
Okay, it appears we're having a little bit of technical difficulty with Dan's microphone. Dan, are you still with us?
Yeah, John. I'm locked up here. My screen is doing nothing.
Okay, let me try advancing the next screen for you and see if you can see that.
All right. So looking at some of the actual data from the soil solution samplers, we had a surprise here. This is both for the cultivar Duke. The dark red is with the sawdust, the light red, the orange is with the weed mat. And what you see here is that we've actually got higher pH under sawdust than without the sawdust under the weed mat. So this is interesting. It's 1 year of data, but it suggests that sawdust may not be providing as an acidic of an environment as it is reputed to do so. Next slide, please, John. Also, we're seeing very, very low salt levels, even with the highest rate of fish. The units here are microsiemens per centimeter, so the level where we would expect to see a problem with too much salt is 2,000. So these are certainly of no concern for too much salt under either of the mulches. Next slide. With the PRS probes, looking at the contrast between the weed mat and the sawdust, we see lower nitrogen levels under sawdust during the May and June, the first part of June, and then we see an increase with the sawdust tending to be as high or higher than the weed mat later in the year. So this might be part of the immobilization phenomenon, that we have nitrogen that's going in, being immobilized by the sawdust and being released a little bit later. These dots up at these arrows up at the top, those are the dates where the fish was actually applied. So we're bracketing all the time that the fish was applied in the field and also continuing for a while after that. Next slide, please. One of the interesting things we're seeing for a number of nutrients is a pattern like this where weed mat and sawdust have similar levels early in the measurement period. During the last 2 to 4 measurements, we see an increase in the nutrient levels under the sawdust. This is interesting because we'd expect for something like manganese the availability to be greater when the soil is more acid. And we saw earlier that it's actually higher pH or less acid under the sawdust. So next slide, please. So we think that that's due to a chelation effect, which I'll talk about in a minute. So overall, we're seeing relatively consistent values for nitrogen under both of these mulches. Under the weed mat, we're seeing more consistent values. Under the sawdust, we see values that are a little bit less than or the same as under the weed mat in May. And then later in the measurement period during July, we see higher levels for nutrients such as phosphorus, sulfur, iron, manganese, and zinc. Next slide. Reviewing from the Rhizon data, we saw that the sawdust mulch increased the soil solution pH quite a bit by 1 unit toward the end of the time that we did measurements. But it also increased the supply of these micronutrients, iron, manganese, and zinc, which are pH sensitive. So we don't expect that as a factor of pH. So our working hypothesis explanation for this is that perhaps this is a chelation effect that is because of the organic matter present in the sawdust mulch breaking down and giving us some small, giving us some chelation to hold those nutrients in solution in an organic complex. Next slide, please. As far as nitrogen goes and the grower objectives, what we're showing, and the other researchers will give you a lot more information about the plant response, but some pretty good yields are being produced on these plots, and we're finding that the nitrogen supply is low to moderate. Very low salt levels in the soil solution, as we might expect under organic management, and this is confirmed by low concentrations of nitrogen in the soil solution. I didn't show you all that data today, and also the PRS levels being in the low to moderate range according to our experience. Next slide, please. So this kind of reviews the, or brings to a close our presentation on the underground investigation. I wanted to point out that, next slide, that this is, there'll be another webinar having to do with this project on March the 9th, and that will feature Dr. Bryla and Dr. Strick, and Handel Larco, who's been working with Bernadine on the plant data. So they'll be talking all about how the plants are responding to these treatments that have been imposed in the field. And that webinar is part of the farming series of eOrganic webinars. This one was in the research series. So with that, I thank you for putting up with the technical difficulties we encountered today in the presentation. And at this time, John will take some of your questions and try and puzzle us with what could be the answer to them.
Great, thanks Dan, thanks Ryan, thanks Louise. We do have some questions coming in. For those of you on the webinar, you should have a question box on your little control panel. You can start typing questions in there. A couple questions coming in. Dan, you said that these pH values were coming from the soil solution. Would that be the same as if you sampled the soil itself?
Well, as you know, all measurements are not the same, even if the name of the measurement is the same. So all pH measurements are not created equal. But we think that the relative values we see here, with the sawdust giving us a higher pH than the weed mat, we think those will be reflected in the actual normal soil testing measurements. But we've yet to bring all this data together and look at it carefully, so I'm getting ahead of myself there. But other studies I've looked at in the Willamette Valley, where they measure both soil solution pH and the pH of the soil, they tend to correlate pretty well.
Okay, thanks. And you guys may not be organic certification experts, but we have a question about whether or not the sulfur would be allowed to be used in an organic system.
So I will make an answer based on what I know, and then perhaps Ryan can chime in if I'm leading you astray. I believe the sulfur that Ryan's been using in his experimental work is actually a product that was identified by our one of our local vendors as being organically certified or acceptable for use in an organic production system. And I think the general rule with any kind of fertilizer or soil amendment product, as far as organic is that you always want to check with your with someone that is actually an authority on this. So some forms of elemental sulfur are probably okay for organic production, and some forms are probably not. It depends on the details of how that product is produced, whether it's considered synthetic or non-synthetic.
Great. So I have a couple questions about using pine straw as a mulch, and whether that be a good substitute for the fir that you were using, and if you have any knowledge of does the soil pH change from using pine straw as a mulch?
I don't think that I have any direct experience with the use of pine mulch, but I believe it is used widely in the southeast U.S. as a mulch for crops like blueberry.
Mm-hmm. Great. Are you measuring another question about soil moisture? Are you measuring soil moisture with the raised beds? And if so, do you have an idea of what is a more optimum soil moisture for the blueberries?
So I'm going to let Luis talk about that. The short answer is that there are a lot of soil moisture measurements, and that the irrigation is actually managed based on keeping the soil moisture in a certain range. Luis, do you have any things to add to that?
Yes, we're using TDR probes. Those are rod probes that are actually buried into the beds, and we have, well, not all the beds, but we're monitoring some of the beds, some of the blocks, and we have every 5 centimeters, we have from 5 to 45 centimeters probes. So we're monitoring the soil moisture in those beds. And well, I don't have any results here with me right now, but we try to keep all the treatments with the same moisture level.
Yeah, one of the advantages of the system that is in place here, you can actually see it on the slide that is here at the end. You can see 2 irrigation lines, one on each side of the row. So it's possible to run those for any length of time based on the soil data. So this was chosen specifically because of trying to keep things as close to the same moisture as possible. And actually, because of that, there is more water that gets applied to the raised beds than to the flat beds, because the raised beds tend to drain more rapidly. The moisture is lower in the raised beds typically. So that some of the correction for that is to apply more water to those beds.
Great. And we do have a comment that came in from another listener that in their system that they found that pine needle mulch does actually lower the soil pH in their system. I also had a question that came in about the research facility itself. How big is it, and can you describe a little bit about where the research is taking place?
So the research is taking place at the North Willamette Research and Extension Center. This is a OSU experiment station located approximately halfway between Salem and Portland. The trial itself, I'm going to say it's around an acre in size, perhaps more than that. The soil at the experiment site is a Willamette silt loam, which is one of our better soils for blueberry production. Holds water, but doesn't have too much clay, so the drainage is still pretty good, even under these flat beds. At this particular site, the soil pH was around pH 5 when the project started, so it was in a good range for blueberry production.
Great, thanks, Dan. And Ryan, maybe you can address this question about the horse manure compost. Was it kind of a sawdust-based horse manure? And if so, do you know anything about the composting process?
I think it was sawdust or pellets made from sawdust that they used for bedding. And I believe they just piled it up and let it sit for a couple of years on that particular one that I had in the slide. So it's basically just really passive.
Okay, great, thanks. early question came in about coffee grounds. Have you seen any work done with that, and if that would be could be used to acidify the soil for the blueberries?
So I have not seen a lot of work with actual research trials with coffee grounds. I've seen a few analyses of the coffee grounds themselves. And from what I recall of those analyses, the pH of coffee grounds was typically around pH 6. And so I don't think they would be particularly acidifying. One of my graduate students, during his time here, he worked with coffee grounds and did a little experiment where he looked at how much nitrogen is released from the coffee grounds and what their decomposition rate was. And in 2 weeks, my recollection is that the coffee grounds are pretty stable. They didn't decompose very much at all, and they didn't release a lot of nitrogen either. So my conclusion based on that limited information is the coffee grounds are more of a soil amendment rather than a a high-strength fertilizer. I think they have maybe 2% total nitrogen, so the carbon-nitrogen ratio is about 15 or 20. So that's what I know about coffee grounds.
Great, thanks, Dan. I think that's all the questions. If you have any final questions, please type those in the next minute or so. Okay, I'm not seeing any new questions coming in, so I think that's going to, oh wait, let's see, here's a late question. How about poultry litter? If someone has a lot of poultry litter in their region, would that be acceptable for use as a fertilizer for blueberries in an organic system?
So poultry litter is probably not going to be that useful for blueberries except in very small quantities. And I'm not sure you're going to be able to spread it in a small enough quantity for it to be useful. The reason why I think that it's probably not an ideal material is that the pH of poultry litter, because it's got a lot of ammonia in it, tends to be around 7 or greater. Because of that higher ammonia concentration, you have the potential for actually causing some injury to plants from ammonia toxicity. And then the third thing is that the salt level is often pretty high with most litter. So I would go really easy on using litter as a potential input.
Great, thanks, Dan. With that, I want to thank everyone for joining us on this webinar. I want to thank our speakers today. If there's anything you missed and you'd like to hear it again, we did record this webinar, and it will be available on the eOrganic website at www.extension.org/organic_production. On that website, you can also find out about our upcoming webinars. I want to thank everyone for coming today.